Okay, Bismillahirrahmanirrahim. So this is going to be the lecture on AC meters, and I'm going to go through on how we use the principle of D'Arsonval meter, and with the combination of a diode, we can use it to measure AC voltage and AC current. Okay, for the learning outcome for this chapter, by the end of this chapter, the student should be able to, number one, explain the principle of half wave and full wave rectifier to measure AC waveforms. Number two, calculate measurement parameters for half wave and full wave rectifiers. And then finally, to explain the concept about AC measurement principles. Okay, now when we talk about rectifiers, actually we are talking about diodes. Okay, and some form of diode configuration. We can use diodes to rectify a circuit in the sense that we can use it to convert from AC to DC. Okay, by definition, diode only allows current to flow in one direction and blocks the flow from the opposite direction. So the symbol of a diode is given in the figure here. Now, the figure shown here is actually a full bridge circuit that consists of 4 diodes connected in this configuration. But we will go first for half wave before we go towards full wave. And when I'm talking about diodes, we are talking about this component here. Okay, for this circuit, which we will see later, we want to convert the AC waveform into its DC equivalent. So diodes are typically made from silicon and germanium, okay, materials that is used to make diodes. However, silicon is preferred because of their low reverse current and high forward current ratings. Okay, so if I were to analyze the circuit, then we need to go towards first understanding the principle of AC waveform. Before we go towards the principle of AC waveform, let's study a bit about the basics of a diode. Now, let's say I'm using silicon. So silicon has a forward voltage of around 0.7 volts. So that means between 0 to 0.7 volts, the diode operates in a non-linear fashion. So during this part, the meter will have low sensitivity. So if you look at the graph here, so we have the part from the starting until the part here, we call it as a non-linear region, and afterwards we call it as a linear region. So for a silicon, this non-linear region is the region between 0 to 0.7 volts, the amount of voltage that needs to overcome the resistance of the diode. After 0.7 volts is reached, then it is going to operate linearly. That means the more current or the more voltage we apply, the more current will flow. Okay, diode to a certain extent is also affected by temperature. As temperature increase, resistance decrease. Okay, bila suhu makin meningkat, rintangan akan makin berkurang. And when we reverse bias, the diode exhibits capacitance properties and tends to bypass higher frequencies. So for every 1 kHz rise in frequency, the meter may show a reading error of up to 0.5%. So the higher the frequency is going to introduce more error. But for typical power system application, our frequency is quite low. When we want to measure, the frequency is below 1 kHz. So it's not going to have too large of an effect. All right. So a typical basic configuration of a general rectifier, we're talking about a half-wave rectifier, we will see this type of figure. So this type of figure, so we have RS, which is the multiplier resistor, and then we have diode D1. So diode D1 here is what is going to filter the waveform, the voltage, and the current waveform. And then we have a shunt resistance parallel to the meter in order to control the amount of current passing through the meter. And then we also have a second diode, diode D2. So diode D2 is used to conduct during the negative half cycle. So I will show you I'll show to you with a schematic representation after this. All right. Before we proceed towards understanding the principle of AC voltmeters, we need to first make sure we understand AC and DC supply properly. So let's take an example of a typical single phase supply, the supply that you use from your power socket. So from TNB, the single phase supply is 240 volts. Now, if you take a meter, a multimeter, and you measure between the two terminals, the live and neutral terminals of the supply, then you'll get the reading of 240 or somewhere around this value. So actually, 240 is what we call as the root mean squared or RMS value of the power supply. When we talk about AC supply, we are talking about a supply with a sinusoidal waveform like the one shown here. So we have one cycle, one complete cycle at any given time. The value always changes according to this cycle here. And the frequency for our supply is 50 Hertz. So 50 Hertz means in 1 second, there is 50 complete cycle like this one. So as you can imagine, in 1 second, there are 50 cycles. And at any given time, the value, the exact value of the voltage is going to change. And it also has a positive cycle and a negative cycle. So when we talk about 240 volt RMS for AC, we are talking about its equivalent value in DC. So DC is given by the graph here. So for a DC supply, when we say 240 volt DC, that means the voltage is always constant at 240 volts. Whereas for AC, it's not constant. It will always change with respect to time. Okay, so RMS value allows us to find the equivalent value for AC, the equivalent value in DC. So as you can imagine from the graph here, the 240 volt RMS is going to be the equivalent for 240 volt DC. So the peak value must be higher than the RMS value for it to be able to produce 240 volts. So you need to understand the difference of the terms here. So we have the RMS value, the peak value, the peak to peak value, and the average value. So this is the part I want to cover next before I proceed with the lecture topic. So let us go to the whiteboard to explain this concept. Okay, hold on. Okay, so let's first discuss about the concept of a diode. So the diode, we can label it or draw it something like this. So you have a triangle. Okay, so let's say I put a resistor here. and then I put a supply. Okay, now the first condition, let's say we have a DC supply. So a DC supply, that means the waveform is going to be flat here. So let's say this is the voltage and this is the time. So the voltage is always going to be constant throughout the time. So there will be current passing here, and the diode will only allow the current to pass in this direction. If we were to connect it on the opposite direction, let's say we have here now positive and negative, so current will flow here, no problem. The diode will allow the current to flow. Okay, but if we reverse the polarity, let's say we change the polarity now to let's say this one is positive and this one is negative. What will happen is that current will not flow. So the current now is reversed. So the current now is not here. Okay. The current wants to flow in this direction. The current wants to flow in this direction. But the diode will block the movement of the current. So if we to connect in opposite polarity, what will happen is the circuit will become an open circuit. Okay, if we connect it opposite polarity, the diode here will become like an open circuit. So no current will flow. Okay, so under this condition, when we reverse the polarity, we call this as reverse biased. So we call it as reverse biased. Okay, reverse bias means we change the polarity here, previously positive and negative, into negative and positive. So it will block and act as an open circuit. The diode act as an open circuit. Okay, now let me change what will happen if we were to connect into an AC waveform. So now I change this into an AC waveform. So AC waveform, we have positive cycle and negative cycle. During the positive cycle, so let's say this is the positive cycle, this is the negative cycle, okay, this is voltage and this is time. So during the positive cycle, current will flow in this direction. During the negative cycle, currents wants to flow in this direction. But during the positive cycle, the diode will allow the current or the current to flow. During the negative cycle, it will block the current. Okay, so what will happen is the original waveform from the positive cycle and negative cycle, what will happen now is that we are going to get, it is only going to allow the current flowing during the positive cycle only, or the voltage at the positive cycle only. Okay, because this is when the current can pass through the diode and we can have the circuit can be functioning. And when the negative cycle is going to be 0. And then if we were to continue the next cycle, we have the positive again, and then we have 0 again. So we are only going to have the positive cycle filtered by this diode. So that is the principle. Okay, now let's look at the definition of average, RMS, peak to peak, and so on. Okay, so we need to memorize a few simple equations. Let me redraw the figure just now for an AC wave. All right, so here we call it as VP, which is reference to the peak voltage. In some books, they also call it as, okay, they also call it as VM, which is equivalent to the maximum voltage. So I'm going to mainly use VP, but don't be surprised if sometimes you see VM as well. Okay, so the opposite here, the maximum value for the bottom part, so excuse my drawing, this should be equal. So this one should be negative VP. Now the range between these two, if I were to draw the range. Now this is what we call as V peak to peak, because it considers from the top to the bottom. So the first equation is, of course, V peak to peak is equal to 2 V peak. Okay, now we want to know about the RMS value. So our RMS value is somewhere around here. We label it as VRMS. And the equation that relates the peak value with the RMS value is given as V peak is equal to SERT2 multiplied by VRMS. Or because SERT2 is equal to 1.414, we can also use this value to find V peak. So if we have the value of V peak and we want to calculate the value of VRMS, so we can calculate as VRMS equals to V peak divided by SERT2, or is also equivalent to 0.7071 multiplied by V peak. Okay, so this is the second relationship, which is the relationship between VP and the peak value and the RMS value. Okay, and then for the average value, we have another equation. So for average value, it's going to depend. So for V average, it's going to depend. For half wave, the value is going to be 0.3183 multiplied by V peak. And for full wave, it's going to be 0.6366 multiplied by V peak. Now, how do you get this value? Actually, we can derive from the circuit. Okay. How? Actually, we can derive, and I'm going to show you the math derivation later on in a table towards the end of this lecture slide. Okay, so these are the relationship that we need to know. So going back to the example just now, our supply is 240 volts. So the 240 volts, if it's not mentioned directly, the value of the voltage, you can assume that it is going to be RMS value. So our supply VRMS is equal to 240 volt. So if I were to ask you what will be the value of the V peak, so from the equation here, the V peak is going to be SERT2 multiplied by 240. So you are going to get the value as 339.41. Okay, so 339.41. Sometimes you will see, for simplicity, they approximate it to 340 volts. Okay, and for peak-to-peak value, peak to peak, we just multiply 340 multiplied by 2, so we get 680 volts. And then for V average, so we need to apply, it's going to depend whether the circuit is full wave or half wave. If it is half wave, then it's going to be 0.3183 multiplied by 340. Or if it's a full wave, it's going to be 0.6366 multiplied by 340. So we have the answer as 108.22 and 216.44 volts respectively. Okay, so this is how we calculate if we are given a certain a type of value. So when you want to answer the questions related to the AC voltmeter, you need to be careful on determining what is the value given in the question. Is it the peak value, peak-to-peak value, RMS value, or average value? Okay, and you need to use it accordingly. Okay, so going back to the slide. Now we go for the concept of half wave rectifier. So by a simple addition of the diode shown here, D1, we can convert the d'Argensolva movement into measuring AC waveform. But there will be some differences. So what are the differences? Let's look at the derivation. First, we calculate the sensitivity. Okay, so let's say this meter has a current, the maximum current that can flow inside it is 1 milliamp. So the sensitivity is 1 kilo ohm per volt. So let's say first we connect it to a 10 volt DC supply, and when we connect it to a 10 volt DC supply, we get a full scale deflection. Okay, we assume we connect 10 volt DC supply, it's going to deflect to full scale. Now we take out the DC supply and replace it with an AC supply at this terminal here. So what will happen to the circuit now? So the peak value, if the RMS value is 10, then the peak value is going to be SERT2 multiplied by 10. So we are going to get 14.14 V peak. Before I go any further, I just want to clarify, in electrical engineering, sometimes we use the term E and sometimes we use the term V to represent voltage. So what is the difference? The difference is that E is a symbol that we use for the source. like battery, generator, typically the voltage we use a symbol E. And for the load, like resistor, like capacitor or inductor, the voltage across those elements, we use V. Okay, sometimes they use V and E interchangeably. Some books, they don't want to differentiate. The source, they use E. The load, they use V. Okay, so E here represents the voltage at the source here now. So we have 14.14 peak voltage. Now we calculate the average value. So this is a half-wave rectifier because we only have a single diode. So we multiply 0.3183 multiplied by the peak value just now. So the peak value is equivalent to 14.14. So 14.14 we multiply by 0.3183, we get the answer is 4.5 volts. So note that when we connect it to a 10 volt DC supply, the meter will deflect full scale, 10 volts. But when we connect a 10 volt RMS supply, the meter will only deflect 4.5 volts. Okay, so there's a sensitivity difference here. So this means that the AC voltmeter is less sensitive than the DC voltmeter. So it's only about 45% or 0.5 times as sensitive as the DC meter. So we can represent the equation here as the voltage DC is equivalent to the 45% multiplied by the RMS value. Or the sensitivity of DC is equivalent to only 45% from the sensitivity of AC, 0.45. And this one is for half wave. So if you want to calculate the value of the multiplier resistor, so we can use this equation here. Rs is equal to the voltage from the source divided by the current minus the resistance of the meter. So the DC voltage equivalent is 0.45 times the RMS value of the voltage source divided by the current and then we subtract with the resistance of the meter. Okay, so calculate the value for the following multiplier resistor for a 10 volt RMS range. So there are two methods that can produce the same answer. So sensitivity of the meter is given as 1 divided by 1 milliamp, so 1 kilo ohm. So Rs, which is the multiplier resistance here, series resistance. So we can multiply S DC, so 1 kilo ohm per volt. This is actually 1 kilo ohm per volt, yeah, not 1 kilo ohm only, 1 kilo ohm per volt. Multiply by the range. The range is actually 0.5 volt multiplied by 10 volt because it's 45% from 10 volts. Okay, and then you minus the meter resistance. The meter resistance is given as 200 ohms. So you get 4,500 minus 200. The value of the multiplier resistance you need to put here is equivalent to 4.3 kilo ohm. And then the second method, we simply use this previous equation here, the ratio here. So we have 0.45 multiplied by the RMS voltage of the source divided by the DC by the current that is flowing in the meter minus the meter resistance. So again, we get the answer as 4.3 kilo ohms. Okay, so please do this exercise and then prove that you get the answer which is equivalent to 449.5 using the example that I've already shared with you. Okay, now let's look at full wave rectifier. So for full wave rectifier, we have a configuration shown in figure 4.20 here. So we replace the single diode with a full bridge rectifier. We still use the same supply, 10 volt RMS. So the peak value is still the same. But now the average value for a full wave, we get 0.6366. Yes, and then we multiply by the peak value, so we get double which is double the voltage, which is 4.5 times 2, we get roughly 9 volts. Remember, for a DC, we get 10 volts. Now, with a full bridge rectifier, we get 9 volts. So that means for a full wave rectifier, the voltage for the DC is equivalent to 90% or 0.9 times the RMS voltage in AC. And this is the equation for the sensitivity. So better now, the performance 90%, closer to the DC equivalent. Okay, now let's look how full bridge rectifier circuit works. So during the positive cycle, so please refer to the figure on the left here. So during the positive cycle, it's going to go start from the positive part and then goes through this diode here, and then goes through the resistor, goes through the meter, goes here, and then goes up here, and it goes here, and it's going to be going down here, and then going back to negative. It's not going to go back up, it's going to go down, and then going back to negative. So you are going to see this configuration here. So this is the flow of the current during the positive cycle. So it's going to start at positive, current will pass through the diode here, and then go back to the negative terminal. So at this point here, there will be no current passing through this diode because it is going to be blocked. Okay, similarly, at this point here, there will be no current passing here because it's going to be blocked by this diode. So that's why the current will flow only in this direction. During the negative cycle, it's going to be reversed. Now, the negative is going to be turned into positive, positive is going to be turned into negative. Now, the flow of the current is going to be reversed. So, we are going to see this configuration. So, it's going to start here, go up, passes through the meter, and then goes back to the positive terminal. And then, as the cycle repeats itself, this cycle will also repeat itself from the left-hand side to the right-hand side, and so on, until the supply is cut off. So this is the principle of a full wave rectifier. So if you look at the next table, you see the types of output that you are going to get. Okay. So this is the circuit for half wave and full wave. So for half wave, you are only going to get the supply, the voltage, during the positive cycle only. During the negative cycle, is going to be 0. And it's going to repeat itself. Whereas for the full wave, in the positive or negative cycle, we are still going to get the same waveform. Okay, because for an AC supply, polarity is not important. Either is positive or negative. The load sees it as a positive. That's why we see something like this. That's why the full wave rectifier is more efficient, double the efficiency compared to the half wave. Now here is the mathematical derivation, how you get the value of 0.3183 and 0.6366. The derivation is only for one complete cycle. So for half wave, we only consider one complete cycle. But since the waveform we only have from 0 to 5, so we only integrate from 0 to pi. So we integrate this equation, we get the answer is going to be 1 over pi multiplied by the peak voltage. So that's why we get 1 over pi is equivalent to 0.3183. For full wave, so we have 0 to pi, we get one equation, one derivation. And then from pi to 2 pi, we get another part. So from 0 to pi, we get 1/2 of the cycle. And pi to 2 pi, we get the other half of the cycle. So basically, we get 2 peak voltage Vp over pi. That's why we double. We have 2 times 0.3183 and we get 0.6366. And then the average output, again, so for the half wave, the peak voltage is Z2 multiplied by VRMS. So the average voltage is going to be 0.3183 multiplied by Z2. And we are going to get, when we multiply these two, we get 0.45. Okay, and then for full wave, the average value, when we multiply 0.6366 with Z2, we are going to get 0.9. Okay, so this is how we determine the average voltage for full wave and half wave. Okay, so next, calculate the value for a 50 volt RMS supply. So we have a 50 volt RMS. We want to calculate the value for RS here. What is the value? This is the configuration of the meter given. So in this context, we assume that the diode is a perfect diode. There is no voltage across it. If it has a voltage 0.7 volt, then actually there is going to be a voltage drop on the diode itself. When we go into tutorial, we're going to see this. Now we assume there is no resistance. We assume it is an ideal diode. Right, so let's see how the calculation is made. So first, we calculate the DC sensitivity. So DC sensitivity is 1 divided by 100 microamps. We get 10 kilo ohms per volt. So because it's a full bridge, we know it's 90% sensitive. So the AC sensitivity is 0.9 times 10. So we get 9 kilo ohm per volt. And the multiplier resistor is given by the AC range, the AC sensitivity multiplied by the range, so 9 kilo ohm per volt, multiplied by the range here 50 volt, and then subtract with the meter resistance 100 ohm. So the value of the multiplier resistor should be 449.9 kilo ohms. Okay, so using the same example just now, please do the calculation to find the what is the multiplier resistance for this condition when we have a 10 volt RMS value connected to the supply, and you should get the answer as 8.75 kilo ohms. Okay, in this example, so we have a meter that can be used to measure both DC and AC. So let's read the question. So determine the reading obtained with a DC voltmeter in the circuit 4.19 when the switch is set to position A, then set the switch to position B. So position A, the supply is a DC supply. Position B, the supply is an AC supply. And determine the reading obtained with a half wave rectifier and full wave rectifier. So the part here we convert it into either half wave or full wave. Either we connect it with a single diode or a bridge rectifier diode. Okay, and this is the characteristic of the D'Arsonval meter movement. So let's look at the step. The first step, calculate the sensitivity. We get 10 kilo ohm per volt. And then calculate the multiplier resistance RS, and we get 100 kilo ohm. So this is what we get for a DC voltmeter. So the voltage across the resistor R2 read by the voltmeter can be obtained as follows. So the voltage across R2 is equivalent to the principle of the voltage divider that I have shared previously. So we get this value, and the answer we get as 4.76 volts. Okay. Now, so the reading obtained with AC voltmeter using a half wave rectifier, so the sensitivity is only 45% from the DC sensitivity. So we get 4.5 kilo ohm per volt. And the multiplier resistance needs to be 45 kilo ohm. We repeat the same process, and we find that the value that is going to be read is 4.499 or roughly 4.5 volts. 4.5 volts, correct. And then finally, when we have a full wave rectifier, it's going to be 90%. So we get 9 kilo ohm per volt. And the multiplier resistance needs to be 90 kilo ohms. Again, we apply the voltage divider rule to get the value for the reading from the AC voltmeter is going to be 4.73 volts. So as can be seen that AC voltmeter using half wave or full wave rectifier has more loading effect than DC voltmeter. That's why the reading is much lower than the expected value. So if you go back, if you use the DC voltmeter, it's going to be 4.76. You use half wave, it's going to be 4.499. If you use full wave, it's going to be 4.73. Okay, a bit off. Quite accurate, but slightly off from the actual value that you're going to get using DC. So this is an example when you have both DC and AC. Okay, finally, I would like to go into the topic of multi-range AC voltmeter. This is just a bit on the theory. So multi-range, we can also convert using the principle of multi-range DC voltmeter. So you have already seen this figure for series multi-range DC voltmeter, where we can connect the resistor in series and we can arrange in such a way to measure different voltage ranges. So we can convert through the use of diodes, D1 and D2 here, we can convert the DC multi-range voltmeter into AC multi-range voltmeter. And we can put the shunt resistance in parallel to the DR Somval meter to improve the rectifier operation. Okay, so this is the essence of the topic for multi-range, for AC voltmeter. And by extension, AC ammeter as well. But we are focusing only on AC voltmeter. Okay, so this is for our class. Any questions, you are welcome to ask me in WhatsApp or in the channel, preferably WhatsApp, so I can address it later. So thank you for your attention, and see you guys soon, inshallah. Assalamualaikum and good day.